Hello, thank you for this warm introduction. Hello, participants. Thank you for joining this session today on the Ciklum Dev Talks. Like it was said, my experience as Ciklum is rather vast. I've actually been with the company since 2013. Have occupied several roles. Most of them were technical, although probably majority of the people around right now would still remember me as head of .NET. Today, I would like to show you a rather extensive demo of how several machine learning-based tools could be used together to make something more interesting, or at least more technically interesting, beyond a simple web interface to an LLM, beyond simple chatbot. That's where the distributed inference comes in. I will introduce you to the more fundamental basics of what I'm going to talk about shortly, but just a few disclaimers to set your understanding and expectation for the next 30 to 40 minutes. All the demos I'm going to show now are equally possible to achieve in the cloud environments on a really low-end devices like Raspberry Pi. The source code for the demos I'm gonna show will be available for you to freely download from my GitHub, and the link to it will be presented here in the slides and also shared retrospectively as a follow-up to this session. So let's dive in. Let's gradually move towards those demos, which I think are the most interesting parts. I was already introduced, thus I'm gonna skip this, but let me pause over for a little bit of agenda. I'm going to briefly cover the state of edge device capabilities when it comes to machine learning workloads inference. I'm going to show you a demo how we use voice activation with machine learning backing the tool. And then we're going to do a more or less trivial speech recognition, also using machine learning tools freely available. And then we're going to use a standalone process accessed via network, which will act as a network-connected backend agent talking to an LLM inference to respond to what we verbally ask it to respond to. So it will become more evident and clear once I do the demo, but we will be stopping across those three parts: voice activation, speech recognition, and small language model inference. What I'm gonna say now, I'm gonna segment the available hardware into a lower end and a higher end edge devices. This is rather subjective because in real business setup, businesses would usually easily be able to afford higher end inference tools and hardware. Therefore, lower end is probably only for the cases where we need to have AI with a lowest power consumption. But this session is not about trying to get into the details of how much tokens we can infer from a small language model, given that we only spend 2 watts per hour. And that might be the next session we hold. But in general, I think worth noting that the LLM and in general, ML inference devices can be segmented into two sides, lower end, higher end. Raspberry Pi, Google Coral processing unit, and NVIDIA Jetson Nano, which is a very outdated dev tool, can be set on the lower end. The modern benchmarking unit is TOPS, tera operations per second. This is a very, it's not like meters per second or whatever. It's not very distinct measure unit, but still the capability of hardware when it comes to AI inference right now is measured in TOPS. And I would just like you to notice the difference that Raspberry Pi, when doing a pure CPU-based inference on machine learning models, usually we're talking about neural network type inference, we're getting basically half of TOPS. Basically, it's 500 what they called GOPS or whatever. So it's lower than basically one top. And higher end devices such as new NVIDIA Spark, it basically boosts your capability to 1,000 tops. So the difference in inference possibilities are dramatic, and the difference in price between Raspberry Pi 5 and NVIDIA Spark is not, it's not 1,000 times more expensive. It's maybe maybe even 20 times more expensive. Well, it's not that it doesn't matter too much right now, the price of these devices. What stands out are Apple set of hardware with their metal GPUs. Your new Mac Minis with M4 or modern MacBook Pros, they are pretty great inference machines using tools like Ollama or other user available tools for LLM and SLM inference. We can see how fast the inference actually can be if you get an Apple device. So although Apple as a company has not yet unraveled itself as an AI powerhouse, the hardware they produce is very capable in the age of AI inference. Just a few more words on what lower and higher end devices are usually used for. And for those of you who are interested more in a real business domain, the business cases that we see in Ciklum, which probably represent the real demand on the market, is for higher end device inference. And we're talking custom machine learning models, custom small language models with custom data layers on pre-trained on top of those. So in general, what business, technical implementation of this in real business, not in this demo area, which we're in during this session, lies in adding your own specific domain-specific knowledge to small language models like Microsoft's Pi 4 or other models which are good for retraining and post-training activities to add your own data to it. And businesses happily ready to use higher-end devices. I'm not touching into, basically I'm not touching at all computer vision aspect, which is the very fascinating and interesting to me. But in general, business can afford higher end. I have not seen a business case, at least in my current work, where the lower end device would be mandatory for machine learning inference. But it can easily be the case for particular startups or businesses who are looking for a low-powered ML inference. Let's dive into example, because I think that's more interesting and more important for you as the listeners today. Obviously, throughout the session, feel free to ask questions. We'll cover them at the end. I want to say a few things before I actually switch to the console and we'll start doing the demo. The knowledge sharing events, which I usually hold for Ciklum or outside, I tend to focus on source code a lot. And with this session, my decision, my strong point was, we will not be looking at source code. Let's just do the demo, talk around what technology is powering this. And for any source code review needs, the viewers can just pull down the GitHub repo. And well, you probably will not be doing it manually. You'll use GitHub Copilot if you will want to do it on the web, or if you can use your coding assistant of choice to break it down how my demos work. If you are interested in replicating any of that, it's all open information. I'm not showing any novel stuff here at this point. I'm basically assembling an interesting setup given the tools we have available. So voice input and command activation. Before I actually started reviewing preparing for this demo, when I had this idea of what I'm going to show you today, I was interested in a topic: why wake word detection libraries, tools, and actually models are even there. Because can't you just do a wake word detection with your pure speech recognition? If your listening application, which has a such a small footprint in memory, up to a gigabyte of RAM, can actually listen to you say anything in a selected language, why do you even need a wake word detection? And I know not all of you are probably completely with me on what I'm talking about right now. So let me break it down again. We're going to see a demo where I'm going to train a model for a custom wake word. We're going to do it right now. The wake word, once detected, will switch the system into a speech recognition mode, and it's going to listen for my input, a question or a task. After speech recognition happens, it's going to offload over the HTTP the message I'll be speaking onto the AI agent, which is running as a separate process. It can be easily running on a different machine, but for simplicity of the setup, it will all happen on my computer here. And the AI agent will actually process using React paradigm. It will reason, think, it will choose actions to make based on what I ask it to do, and it will output the response back to that application which did the speech recognition. We will not be doing text-to-speech synthesis, but that's trivial and possible to add on top of that. So why wake word? For some of you, it's obvious. Maybe I had this hint in my mind when I started, but the amount of resources required to do a rather quick and permanent wake word detection is much lower than you would need to use if you were to do a full-blown speech recognition. Therefore, in my demo, these are two separate things. We will train the wake word. The application will be waiting for me to say this wake word, and only then it will turn on the microphone to pipeline the audio data into a speech recognition, which obviously is not limited to the wake word I'm gonna train for. So let me share my my console, and I have 3 columns here, and the most left one, maybe it's the most right one for you, probably left, is the coding assistant. It's Claude Code. Never mind, we're probably not going to use it. So 2 essential elements of my demo are the inference agent, which is linked to Llama on this machine, and the actual audio model. I'm running inference agent. The source code for these tools is available on GitHub. I'm gonna just run the agent so that the listener there, and once our voice, the tool that deals with voice is ready to communicate to it, it will just have an endpoint that works. By the way, the current model, which is loaded, is Gemma 312B, so it very well can be considered a small language model. The agent here, and you're gonna see it reason and respond to my audio activated client, does almost full React. It basically reasons about the request I'm giving it. It chooses either to provide a final answer or do a tool call. It does a tool call, evaluates its observations about the response of this tool. I'm going to show it to you. It's going to be more vivid on the demo. Let's do the audio part. Let me start the Python script, which is essentially the application. Before the session, I've been testing it with a custom wake word, which was Hello Friday. And we need to basically train a new one. I could have used Hello Friday, but then I don't show you how easy and fast the training is on the MacBook Pro. So that's the hardest part. I need to figure out the word. So I'll say it's going to be hello Sunday, the day after tomorrow. Now, bear with me. I'm going to be saying hello Sunday 5 times. It's going to be rather awkward, but it's not going to take us longer than probably 20 seconds or so. Once I have provided 5 of my samples how I say this wake word, the script is going to do the synthetic word generation, synthetic audio generation on the background, so that the wake word model that we train has much more than simply 5 samples. Otherwise, it will not do a good job doing the wake word detection. Let me show you the demo, and probably then I'll cover you some details, or maybe some details will be undeveloped during the question session. So I've chosen the wake word to be hello Sunday. Let me train it. Okay, I should be saying it. Hello Sunday. Hello Sunday. You know what? There is a problem. My microphone is right now occupied by Zoom, a Zoom that I'm using to communicate with you. So this kind of breaks my demo. Let's see if I have the voice part ready. Oh no, I don't have it. That's an interesting situation. Give me a second, guys. That's a real technical challenge we're seeing here. Let me mute my mic and see if it will become available to my system. So never mind the silence for the 20 seconds. Please relax. I'm going to try to do this recording and then I'm going to unmute and continue talking to you. Okay, I'm going to explain what's happening here. That's very interesting. Nope, it's not working because Zoom is occupying my microphone. Let me try a different one. I'll switch to my, just a second. No. So it's interesting. The situation where I basically need to disconnect and reconnect. I didn't expect this to happen. Let's see. Can you recover my previous wake word recorded? As I'm having trouble with my mic. Let's see. It would be such a shame if I don't show you the full demo. I think in order to do it, I'm going to need to disconnect and reconnect, but that's the worst case scenario. Let's see if AI agent is able to actually recover the session I have. Oh, cool. Let's do. Can you make hey?
Disconnect for 2-3 minutes. That's fine. We can allow that to make sure that you have a proper demo ready.
Yeah, and by the way, thank you for saying that. I'm gonna do it in case my Claude Code is not able to recover my previous ones. So let's give it a try. I'd hate it to disconnect from the
No
session
problem.
and then reconnect. But let's see.
No problem at all. Just let me know, just in case. All right.
Sure. But thank you for listening. You clearly understand the challenge I'm facing here. One microphone. If I were actually doing this on a separate device, I wouldn't be in this situation because the microphone would be free. Okay, let me try again. So, hey Friday. So guys, I strongly encourage you, even though we had this little hiccup right now, to try the source code I'm sharing and to see the speed at which you can train your own wake word on your computer. All the instructions are there in the source code repo. The training on an M4 CPU, GPU on the MacBook Pro happens basically within 30 seconds. So it's very fast. On Raspberry Pi, it takes 3 minutes to train a custom wake word in the setup. I have like settings I have in the code. But for now, we need to omit trainings because I simply can't. Oh no, it's not gonna listen. Okay, guys, bear with me. Let me see if my demo works now because microphone will still be a problem with this. Hold on. I use existing model. Yes. Okay. So, hello. Hey, Friday. Oh, it detected. Great. You see, it does the recognition. Let's do the normal. Let's do the normal demo now. So we know that the problem we faced is only at wake word training stage. assume that we trained "Hey Friday" as the wake word. It will not, the script will not be reacting to anything else. I'm going to say, yep, and it's now listening. And the moment I'm going to say the wake word, I'm not saying it not to trigger it, it's going to actually start speech recognition. The agent here is just waiting for me to finish saying things in the voice module so that it can process. I'm going to say a wake word now, and I'm going to give an agent a task. So bear with me. Hey, Friday, what is the weather in San Francisco? We can see an agent actually pick up the request. It has a synthetic tool called getWeather, and it has called this tool from the source code, and it has provided us the response. It basically just told us, okay, it keeps on doing the okay, and now it's back into wake word. That's great. Anyways, let's review what happened here, because that's important. I have said the wake word and I asked it, what is the weather in San Francisco? And it has actually called the internal tool and generated response and sent it back over the network to appear here. That was the first response here. The weather in San Francisco is sunny, blah, blah, blah. That's a synthetic tool. Now let me say, hey, Friday again. List files in the current directory. Do not use recursion. All good. It's working. Here it is. So I will not be saying the wake word, but let's review what happened here, because it's no longer a synthetic tool call. It was a real one. I basically said, list files in the current directory, do not use recursion. I did not type it. Speech recognition module actually picked it up. It has coerced so basically the speech recognition module I'm using, it's called WOSC, and it listens to me, it infers what it hears, and then it maybe fixes some things which are common mistakes in its model recognition. So list files in the current directory, do not use recursion, was something that was a request into our React agent. React agent thought that it analyzed the request, and its decision was to call shell command lsl. It did call it. It was important to tell it not to use recursion, otherwise it might have assumed it needs recursion, and it would have simply generated us a huge response. For the demo, it's bad. So it analyzed the files in the current directory, and it has responded those in a form of a final answer over the network. So this was the agent's response. Now let's quickly review what happened. And by the way, I hope you have seen how fast it was. Yes, there was like a moment or so, maybe 8 seconds, when we were waiting for step 2 to finish, but it wasn't even obvious when the response was sent back between the columns here, because it continues to listen. Interesting. You see how much it has listened. Let me stop it. So that basically brings us to the aspect of the topic, which is the orchestration. Let me break it down which orchestration happens here, because by this time on the screen it's a mess, and not all of you are able to see all of the details from the screen well, but all you need is to listen to me describe what's happening. We have a classical conventional application that uses 2 machine learning tools, wake word detection using open wake word, and speech recognition using WOSC, in order to orchestrate a process of being activated only by a given wake word, which we, by the way, can train. That's the only thing that didn't work. The microphone was not captured because it was occupied by Zoom when we did the training. Maybe I even assumed it doesn't work. It might have actually worked because speech recognition, as we have seen, works well. So in any case, orchestration is conventional application part of the script. We kick off the wake word training, then we listen for the wake word. Once it's detected, and by the way, you can see that the confidence of the detected wake word is rather low. So the system is only 35% confident that I actually have said, "Hey, Friday." But my tests show that almost anything above 35 will not introduce false positives. It will actually work pretty well to filter out everything unless you say an activation word. After this, the script kicks in and different neural network inference mechanism, which is WOSC. And this one is trained to detect any English language speech, or I can choose a different language, load a model, and it will work equally well. And only after it hears a pause that I have basically finished speaking something, it will make a normal conventional HTTP request to localhost port 8000, where our agent is listening for requests, to simply parse what was said. And the agent, it's a topic for my previous knowledge sharing event in Ciklum, where we reviewed how different approaches to build React agents without using third-party tools like LangChain, LangGraph. As you will see, if you end up inspecting the source code, this React agent is purely Python agent. There are no imports, but actual language model inference happens via Ollama. So 3 neural networks worked here to make this possible. Wake word detection network, speech recognition network, and small language model inference on a different process. Orchestration between them, the fact that we were saying things verbally and agent was thinking about those and returning us the responses, that's the orchestration which in any form, any tool, any wearable device, smart home, things like this happen under the hood there. There is no magic here. I believe still LLMs feel like magic. Everything else is just conventional programming. But it's still quite fascinating how efficient all of this can be while only running here locally on a simple machine, which is a work laptop. And I can tell you on Raspberry Pi, it is not much more slower. Yes, inference obviously is slower, and if you do orchestration, you probably should do LLM inference either in the cloud or in a more capable edge device. But things like Raspberry Pi are more than enough for wake word detection and speech recognition.